Hey everybody, welcome back. As promised, in this video, we're going to cover two more of the addressing modes, being absolute and symbolic. So these are two more of the 7 in total. So just, as a reminder, addressing modes, they're a way the source and the destination locations are specified in the operand of the instruction. And the MSP430 supports 7, so here are 2 in this video: absolute mode addressing and symbolic mode addressing. There's nothing special of these two, although they do go together, so it makes sense to put them in the same video. But the others are covered in other videos. And again, I want to remind you that the amount of time the CPU takes to execute an instruction depends on the addressing mode. And I know that because I read the documentation. All right, so we'll start with absolute mode, and then that's going to actually set us up nicely for symbolic mode. Now, absolute mode is when either or both the source or the destination is the actual 16-bit address value. So we have to know the address value, and so really absolute mode addressing is not used a lot in practice for that reason. To signify an address, we're going to put an ampersand in front of the number. And so that's going to tell the assembler that we have an address here, not like some hexadecimal or some sort of data, right? So this is the first mode that allows us to access the memory system. If you recall, register mode was doing just that, accessing the registers, R4, PC, SP, right? They were not, that was not a mode that allowed us to access the memory system. So again, because we're accessing the memory system, then we need those, we need to know the addresses. So again, the instruction is going to operate on the data held within the addresses provided, not the address, the actual addresses. It does not operate on the addresses. It's operating on the data provided by those addresses. And we're using the ampersand, and in the MSP430 documentation, the absolute mode is denoted as ampersand ADDR. Okay, so the best way to go about learning absolute mode of addressing is with an example. And before we get to that example, I want to point out something that's very important now. We kind of sidestepped it a little bit, but we can't any longer. The MSP 430 6989 begins its data memory at address 1C00 in hex. And I know that because, again, I consulted with the documentation, and there it is. The word RAM here is technically incorrect. It's actually read-write memory, but colloquially known, it's colloquially known as RAM. It's just kind of adopted now by Texas Instruments. So there's the data memory. It's actually read-write memory, but they're calling it RAM there. So there it is. It starts at 1C00. That's the important part. So, okay, our example. Let's say the goal of this example is that we want to begin with some data in memory. And so there's our address, right? The addresses start at 1C00. And so we want to start with, let's just throw some data in there, 1, 2, 3, 4 in hex. And also the next even address, 1C02, let's throw some data in there, cafe, C-A-F-E. So we want to start with that in this simple example, and then we're going to perform some instructions, and we want to essentially copy or move data from one address, the 1C00 to 1C04, and then from another address, 1C02 to 1C06. All right, so here's some example code that I have up here. And you'll see that there's actually a lot going on in this. There's a lot going on. So first, notice the main block there. Notice some of those items in the operands use that ampersand, like ampersand 1C00H, right? So this is indicating to us that these are absolute mode addressing. Absolute mode addressing uses that ampersand. Notice also that these operands or these instructions are employing register mode addressing as well, right? Like the destination in that first move instruction, that's in a register R4, so that's using register addressing. Okay, so we've got some moves there, and then you'll notice that at the bottom I have memory allocation. We've got a .data directive and then some more code there. So the .data directive allows us to two things: initialize data in memory and reserve space in data memory. And then there's the .retain directive, and that is, if you remember from a previous lesson, that's really keeping the optimizer from getting rid of our code. We're not doing anything groundbreaking here, and we don't want the optimizer to say, hey, you're doing something too simple, let's get rid of this and that and this. So we just want to retain all of this. You'll also see a .short there. That's just specifying a 2-byte data there. All right, and I do want to point out these vars, the lines that start with var1 and var2, that is, the reserving space in data memory. We're going to ignore that for right now, and then we're going to come back to that and say more about like what those two lines are doing in particular. Okay, so upon loading the program to the MSP430, even before the main is executed, those constants down there, those are loaded into data memory. So this is what I mean by beginning with this data. So you'll see in my memory map here to the right, I have at address 1C00, we're moving the data 1, 2, 3, 4 into that memory location. And again, that's 2 bytes, and that's specified by the .short directive. And also then in address 1C02, we're moving cafe, C-A-F-E, into the next available address, which is the next even address. So again, how do I know that? Let me back up. You'll see that I have not specified 1C00 at all in those two lines. How do I know that 1, 2, 3, 4 is being loaded into that address? That's because that is where the data memory addresses start. And I know that from the data sheet. So, okay, so now I know 1, 2, 3, 4H gets moved into that address. 1, 2, 3, 4 in hex, that is, gets moved into that address, and I know cafe gets moved into the next available address. And just remember, you need a 0 in front of cafe to tell it that this is actual like data, right? Okay, so let's move on then. Then we see from those two instructions, this is going to take the data located at that memory 1C00 and move it into register R4. Then the next move instruction is going to move the data from R4 into address 1C04. So you see how I have to know those memory locations, right? I will say that alternatively, we can combine those together and just use one instruction without register mode addressing. So we can just say the source is 1C00 and the destination is 1C04. We could do that, but what I'm emphasizing here is that you can mix and match addressing modes. So I've got absolute addressing mode and I've got register addressing mode here. Okay, and then similarly, the next pair of move instructions do a similar thing here. We're taking the first move instruction in that pair, takes the data from address 1C02 and moves it into register R5, which I'm not showing here. And then the second of in that pair moves the data from R5 to address 1C06. And so we've achieved what we wanted to. The data are there as shown in my memory map. Again, alternatively, those those two instructions, that pair, could be combined into one instruction. Again, I'm emphasizing that we can mix and match modes of addressing. All right, now I want to talk about these last two lines. So we wonder, like, what are those two lines doing? First of all, I want to say that the program will work without these two lines. All right, if we commented those out and we uploaded this program to our MSP430, we would see the exact same outcome. However, the details are a little bit different, and we would like to know those details. What we actually did is we started with this memory map, and this is before main is executed. So those two addresses in memory where I have the commented reserve third word, reserve fourth word, 1C04 and 1C06 respectively, because we reserved them with those two lines. Actually, when the program begins, we've cleared that out. We've got 0000 in both of those memory addresses, right? And we've labeled those addresses var1 and var2. The dot space directive and then the 2 after it means we want 2 bytes or 1 word of space to be reserved. Now, that actually naturally brings us up to the next mode of addressing. That's symbolic addressing mode. All right, in the previous slide, I'll bring it up here. This is the previous slide. We see that I've introduced these labels, that the 2 that I reserved were called var1 and var2. Okay, and here's the next slide. This is the symbolic addressing mode. Here, I go one step further and I point out that the constants 1 and 2 were also labeled. You can see that in the code at left. And so actually when you label those constants, you're actually not labeling the constants per se, you're labeling the memory addresses. So this is actually much more intuitive. This way we don't need to remember the addresses. We just need to use the labels that we're giving to. So this example now, this does the same thing, but using the labels that we set up with the .data directive. So you'll see the first 2 lines in the main block, the 2 move instructions. I've replaced the actual address 1C00 with my label const1, and the second move instruction replaced I think it was 1C04 with var1, right? And similarly, in the next pair of instructions, I've replaced the absolute, see there, the keyword, absolute address with my labels. So when you do that, that's called symbolic mode addressing, right? And say, well, where's the special sign that you need, like the ampersand or the hashtag or whatever? You don't need a special sign. The assembler treats non-numeric characters in the operand as an address label. Okay, so it knows, it sees that and it says, oh, that must be an address label. That's why when you put hexadecimal data in, you need, or it doesn't even have to be data, hexadecimal anything, an address or whatever. If the hexadecimal starts with a letter, that's why you need to precede it with a 0. Otherwise, it thinks it's an address label. Okay, so that's it for absolute and symbolic mode addressing. And next time, we're going to look at the 3 remaining address modes. Thank you.